Okay, so I'd like to jump forwards a little bit. I'm going to jump over our discussion of general relativity and save that for the end of the term, just to make sure that we have adequate time to go over all of the quantum mechanics that I'd like to get through. Um, so today's lecture is quantum mechanics and why we need it. Maybe a subheader for this could be, or how we lost our certainty. Um, so if we were running this class in the late 1800s, end of the 19th century, what we would uh, be telling you is that physics was mostly done, that um, that Newton had tied a nice, neat little bow around this a few hundred years ago, and that the brightest of you should consider a different field because at this point it was effectively stamp collecting, um, trying to get a little bit better uh, certainty on some of the fundamental physical constants. Between Newton and Maxwell, pretty much everything that needed to be done qualitatively was done. It was just kind of figuring out, you know, sig figs. So in the late 1800s, our laws of physics, we had Newton's law of gravity, we had the laws of mechanics, which I think you could uh, credit to Newton and Galileo largely. Um, you had Maxwell's equations, which uh, a few different physicists uh, had developed, but Maxwell had kind of uh, collected them and had demonstrated that you could derive the speed of light, uh, giving credence to the idea that we were looking at electromagnetic waves. Um, that coupled with statistical mechanics, or all of the above, coupled with statistical mechanics, was thought to largely explain everything. And so I think that with hindsight, you know that that's not actually how things turned out, right? There were actually still some outstanding problems that remained, um, and that is going to lead to why we're going to need quantum mechanics. So, by the way, I guess I this is a little bit out of time order, right? But uh, mechanics wasn't complete either, right? We just finished special relativity where you would also need that, but that didn't come until 1905, so um, late 1800s. Um, okay, so what are these outstanding problems that we were aware of, but hadn't, we figured that it was experimental error, um, or perhaps some rounding errors in some of our physical constants. One is uh, is the precession of the perihelion of Mercury's orbit, but uh, that's gonna speak to general relativity, so I'm omitting that one here. Um, but another uh, known issue was this issue of black body radiation. So uh, the ideal emitter and absorber of radiation uh, is called a black body in physics. It uh, because it absorbs all radiation instant upon it, uh, it it appears dark, right? But it also has to re-emit uh, radiation, and uh, and that's our uh, that's our first problem to study. So I took, well, I didn't take this image from Wikipedia. I took an image that I'll show you in a second from Wikipedia, and I kind of carved it up a little. But uh, if you apply statistical mechanics and Maxwell's equations, you get Rayleigh-Jean's law. Rayleigh-Jean's law is uh, is the classical expectation of how intensity of electromagnetic radiation should go as a function of wavelength and temperature. And what you see is that it's some grueling math, and so I'm going to leave that aside. But it's a bunch of fundamental physical constants, 2 pi c kb, multiplied by T over lambda to the 4. Now, maybe straight away you can see the problem here. The problem got a cute name. We called it the ultraviolet catastrophe. Because as you go to lower and lower wavelengths, you should expect greater and greater intensity, uh, so that the object would be giving away all of its energy very, very rapidly through electromagnetic radiation, if this were true. Um, and so classical theory predicted this curve where the intensity is just spiking as you drop wavelengths, right? As you drop to lower and lower wavelengths. You can probably suss out already that that's not realistic, right? Um, Objects around you aren't at the lowest possible temperature. You're not at the lowest possible temperature. So obviously objects aren't radiating away all of their energy instantly, right? Or near instantly. And so if you carry out experiment again at 5,000 K, this is uh, what you classically expect. If you carry out the experiment, what you really get is something like this, where there is a peak at some wavelength, uh, and at 5,000 Kelvin, it's actually in the visible range, right? The photosphere, the sun, um, is, give or take 6,000 Kelvin, um, and so it's not surprising uh, that uh, the peak intensity uh, appears at a wavelength that's in the visible range. Now, um, perhaps even more telling here is what happens if I give you this full image from from the Wikipedia source. Notice that as you drop the the temperature, 5,000 Kelvin, 4,000 Kelvin, 3,000 Kelvin, qualitatively, the shape of the curve remains the same, but notice that the peak value of wavelength is shifting to greater and greater wavelengths. And it can be shown that uh, the wavelength where that peak value of emission occurs scales as 2.898 millimeters times Kelvin over the temperature measured in Kelvin. Um, this is known as Wien's displacement law. Um, let me um, so this is Wien's displacement law. Um, and coming up with an explanation for this, well, doesn't occur in classical physics. 1900, Max Planck uh, is able to theoretically explain the shape of these curves, but to do so, he had to make kind of some slightly unsettling assumptions. First, he imagined that uh, the the black body radiator was composed of many, many oscillators, and that each oscillator had an energy that was quantized. By quantized, I just mean that it comes in steps. Um, so so discretized values. Um, and and so the energy of the oscillators had to go as n times h times the frequency f, where n is some integer 1, 2, 3, 4, 5, so on and so forth. H is our Planck's constant, and f is the frequency of oscillation. Further, he had to assume, by the way, the value of h is 6.626 times 10 to the minus 34 joule seconds. Further, he had uh, to postulate that an oscillator absorbs or emits energy to go between allowed quantum states, and the states differed in energy by hf, by Planck's constant times frequency. There is no uh, is no classical explanation for why you would expect this a priori. Um, but if you do that, you get uh, Planck is able to demonstrate that uh, instead of this statement, right, that I of lambda and t goes as 2 pi c kbt over lambda to the 4, which again led to this ultraviolet catastrophe. Instead, he was able to get to I of lambda and t is equal to 2 pi h c squared lambda to the 5 uh, times e to the hc over lambda kbt, all of that minus 1 end quantity. Um, Now, the nice thing about this is that um, it starts out, so for small values, it starts out like so, and then uh, you can uh, try to convince yourself that this will actually have some peak value. You can take a derivative if you want, set it to 0. Um, and then also note that uh, this will uh, similarly trail off towards 0 as you, well, as you go to greater and greater wavelengths. And so the nice thing about this is it it gets rid of this ultraviolet catastrophe that we had in classical theory, because as you go uh, towards small wavelengths, this term in the exponential gets very, very big, right? As lambda gets small, hc divided by lambda kbt gets very big. So e to the something very, very big is really, really, really big. Minus 1 is still really, really, really big. Times lambda to the 5, uh, well, for a small enough lambda, this exponential term uh, is going to dominate over the lambda to the 5 term. And so this goes towards 0, both for very small wavelengths and for very large wavelengths, which um, matched experiment very well. we also had some other problems with classical physics. So there was the J.J. Thomson plum pudding model of the atom. I encourage you to to look that up. Um, there is the Rutherford model of the atom. Um, so uh, the Rutherford model of the atom um, took or uh, those who worked for him in his lab took a thin sheet of gold foil and fired alpha particles at it. So again, with 21st century hindsight, we know the alpha particle is just a helium nucleus, but uh, the alpha particles um, were able to, uh, many were able to pass straight through the film so that you could detect them back here. He assigned one of the undergrads in his lab uh, to look back here uh, for for alpha particles, and amazingly enough, he found uh, some alpha particles that were uh, backscattered with basically the same energy that they had left with. And from this, Rutherford comes up with the Rutherford model of the atom, which is that most of uh, the the atom's mass is concentrated at the center, which we call the nucleus. That's where the protons and neutrons live, and then you have uh, tiny little electrons orbiting. Now, this is kind of akin to our planetary orbit model, right? Like how Earth orbits Sun or how Moon orbits Earth, um, where there is, instead of a gravitational interaction pulling Moon towards Earth, you have an electric interaction that's pulling the electron towards the positively charged nucleus. The Moon doesn't fall into Earth because it has a substantial tangential speed, right? Um, if the Moon weren't traveling really fast sideways, gravity would pull it into Earth. Instead, it falls around Earth because it's traveling really fast sideways. Similarly, uh, the Rutherford model imagines that the electron has some substantial uh, tangential speed, and that's what allows it to orbit the nucleus. So this is the hydrogen atom, right? Because it only has one proton in the nucleus. Um, the the issue here um, is one that you probably remember from Physics 230. You probably, at the end of the semester, got to a point where you were confident that an accelerated electric charge produces electromagnetic radiation. And this electron is absolutely accelerated, right? It's traveling in a circle, although I didn't draw a very good circle in the Rutherford atom. And so it is constantly accelerated. It should be constantly radiating away electromagnetic radiation, which means it should be losing energy as the light carries energy away, meaning that the electron has to give up either kinetic energy or potential energy, but either way, the kinetic energy is how it's managing to maintain its orbit, or the potential energy is stated as describing how far away it is from the nucleus. Either of those would cause it to rapidly spiral into the nucleus. And so that implies that the atom isn't stable. Well, my Milky Way candy bar breakfast is made of uh, sugar. Sugar has lots of hydrogen atoms, and it was very, very real and very, very tasty. Um, and so I can tell you that the hydrogen atom is stable, and so that spoke to a problem for this Rutherford atom. One of the physicists in Rutherford's group was Niels Bohr, and Niels Bohr recognized this issue, as did many other physicists. But he also recognized that there was enough good stuff in the Rutherford atom that um, that it was at least on the right track. And so trying to shore up this Rutherford model, Bohr added on to this notion of quantization and actually quantized the angular momentum of the electron, producing what were called steady states, so that the electron could only take on specific values of angular momentum. He didn't have an explanation as to why that should be true, but what he did realize is that this explained uh, not just how the electron could avoid spiraling into the nucleus, but it also explained another problem of atomic spectra. Um, and we'll go over this in greater detail later, but um, if you look at uh, what happens if I so you're probably familiar with the name Bunsen from Bunsen burners. You might be familiar with the name Kirchhoff from uh, from your physics 230 days, but Kirchhoff and Bunsen worked together to look at uh, emission and absorption spectra, and let's take a look at Kirchhoff and Bunsen's results. So uh, this image I took from classic Cornell University. Um, so if they took a hot, dense uh, substance and looked at it through a spectrometer, and we'll try something like this experimentally towards the end of the term, or a few more weeks, I guess. Uh, they got a continuous spectrum, meaning all the colors of the rainbow. Note that what I liked about the way that they did this, that this professor did this, um, is they've kind of modeled this uh, under our black body radiation curve, which I thought was kind of a cool approach. Um, this part isn't the interesting part, at least for today. It is interesting, just not for what we're doing at this moment. If they took a sparse hot gas, they got emission spectra, meaning they didn't get all the colors of the rainbow, they only got select fringes. That's interesting. Um, so for the hydrogen atom, let's say, it only, in its neutral state, has one electron, and so you might have expected that it only gives you one bright fringe, or maybe you expect that you could make that thing accelerate any way you wanted, and so you should get all the colors. but only being able to get select colors, frequencies. That's interesting. How does one electron give just select values? Um, Even more interesting, perhaps, is if you took a sparse cold gas and passed a continuous spectrum through it. Instead, you saw the same missing frequencies that you produced if you had a hot sparse gas. So this is what you get if you have a cold sparse means not dense, right? Um, a cold sparse gas yields an absorption spectrum that is missing some of the same frequencies that you get if you have a hot sparse gas. If you have a dense uh, gas or other solid or liquid that is hot, you'll get a continuous spectrum. Well, sorry for if anyone's getting dizzy from my horrible scrolling. Um, Bohr recognized that if he provided quantized orbits by quantizing the angular momentum of the electron, that now he could explain those absorption and emission spectra for the sparse gas. Note that only select values of uh, of light with just the right energy could carry this electron from a lower state to one of the higher states. And similarly, the electron dropping from an allowed state to a lower state would emit those very same energies of light. So Bohr is able uh, one, fix this problem of the instability of the atom, and two, explain uh, qualitatively emission spectra. Now, what we're going to see is that this Bohr model of the atom uh, at first pass does okay, reasonably well for hydrogen, um, although it has some other issues even for hydrogen. Um, but it really struggles once you start looking at atoms more complicated than hydrogen. For that, we're going to need a fully quantum mechanical atom, and we'll spend some time on that. Compton scattering is the subject of our next lecture, but uh, here's where life gets really kind of cool. When light scatters from electrons, it behaves like particles are scattering from electrons. Something even more bizarre is that even though the light behaves like it's a particle scattering from the electron, the wavelength changes. So it definitely is displaying both particle and wave behavior here. But again, that's the subject of our next lecture. Um, so I want to round out our discussion today with the photoelectric effect, because that's what your lab is this week. Um, so in 1905, Einstein's miracle year, right? He publishes 3 papers, any of which were worthy of a Nobel Prize. Probably the thing Einstein is most famous for is relativity. But that was, as you've already seen, crazy enough that uh, it was a little hard to accept. And since you've already noted that it required such incredibly high speeds to show special relativity effects, um, the Nobel Committee knew he'd earned a Nobel Prize. The question was what they should give it to him for, because in physics you don't win the Nobel Prize for a career, you win the Nobel Prize for an individual contribution. and they didn't want to give him the Nobel Prize for relativity and then have it be invalidated. And so he actually wins the Nobel Prize for this photoelectric effect. All right, so what is the photoelectric effect? Well, you probably remember uh, our rough qualitative statement of what it means to be a metal. A metal is a metal because the electrons that are used to kind of bind the solid together, uh, well, not all of them uh, are required to be in a specific location. So some of them are loosely bound, right? Our statement of what makes a metal is it has at least one loosely bound electron per atom. Now, classically, you would expect that if you uh, shine a light onto a metal, since the electrons are loosely bound, meaning that they have a small energy debt, you should be able to liberate some electrons. And so when light was used, pardon, when light was used to photo eject an electron from the metal, you could make some predictions using classical physics. Um, so I've kind of, this is more a mnemonic than anything, but I've drawn the electrons at different depths. Um, and so some of the electrons have an easier exit than others. Um, but uh, one of the things that Maxwell's equations and statistical mechanics would predict is that the dependence of the photo-ejected electron, photo-ejected just means we ejected it using light. It's a fancy way of saying we used light to give energy to this electron to kick it out. The dependence of the photo-ejected electron's kinetic energy on the intensity of light. In other words, uh, the the more intense the light you shine on the metal, the more kinetic energy electrons should be kicked out with. Um, and and classically, since we're thinking of light as a wave, the intensity is going to be described by the amplitude of the wave, right? So here we've got red, small amplitude. Here we've got red with a big amplitude. I tried and didn't do a very good job of keeping the wavelengths the same. Here we've got blue or purple, I don't know which, I'm sorry. Uh, and again, I tried to keep the wavelengths the same, but I tried to draw different amplitudes. So according to Maxwell's equations, the amplitude is the decider for the kinetic energy of this ejected electron. So more amplitude, more kinetic energy. Less amplitude, less kinetic energy. Also, the time interval between light arriving and the photo-ejected uh, electrons leaving would depend upon the intensity of the light. So you're just going to keep pumping energy in either way, and eventually you're going to get enough energy input that this electron can leave. So there's some time delay between when the light arrives and when the electron leaves, and it's just going to uh, take longer if you're using a lower amplitude. Hopefully that makes sense. Um, Classically, you also expect that uh, there should be no dependence of the photo-ejection of electrons based upon the light frequency. It shouldn't matter whether we're using red light or blue light. It only matters about the intensity of the light, right? How bright for uh, a slightly mismatched description, right? Uh, Hopefully that's okay. Um, so if I use a bright red light and a dim blue light, it'll just take longer, classically, for the blue light to eject one of these electrons. Um, or if I use a bright blue light and a dim red light, again, it'll just take longer uh, for the red light to eject the photon. That's what 3 is saying. Um, but uh, uh, you'll still get photoejection either way. It's just going to take longer. So the light frequency doesn't make a difference. It's the light intensity. There's other ones. I'm going to stop with 4. I was going to stop with 3. 3 strikes and you're out, but let's go with 4. No dependency of the electron kinetic energy on light frequency. Uh, Again, it shouldn't matter whether I'm using red light or bright light, red light or blue light. It only cares about how intense the red light or the blue light is. Hooray. When you actually carry out this experiment, none of these 4 things is actually true. Um, so first, if you carry this experiment out, uh, whether you're using a bright red light or a dim red light, you get the same kinetic energy of the ejected electrons. Whether you're using a bright blue light or a dim blue light, the uh, the kinetic energy of the photoejected electrons is still the same. Even crazier is that uh, there is a dependency of the kinetic energy on light frequency. The blue light will kick out an electron with a higher uh, kinetic energy than the red light will. In fact, the only thing that the intensity of the light does is more intense light kicks out more electrons, but it doesn't kick them out with a higher kinetic energy. So brighter instant light means more ejected electrons, but it doesn't mean electrons with more kinetic energy. Time interval. Again, classically you think there's some buildup, right? And so a brighter light should kick out electrons sooner than a dimmer light. Instead, what you see is they both kick out ejected electrons almost instantly. Um, Pretty much as soon as you start shining the light, you start ejecting electrons. So there's almost no delay, whether it's bright or dim. And then the thing that classical physics really couldn't absorb um, is that there actually is a dependence of photoejected electrons on light frequency. There are metals where if you shine a red light on uh, the metal, it will not photoeject an electron no matter how bright it is. And there are metal and that very same metal may actually photoeject an electron with a blue light even if it's very dim. So a bright red light may not cause photoejection of electrons, whereas a dim blue light will. And so this idea that there is some minimum frequency of light that will cause photoejection of electrons, classical physics was stumped. There isn't a good explanation here. Einstein looked at this and was able to explain it, but again, it required um, a wholesale change to classical physics. Um, Einstein has the wave particle duality, that light travels like a wave, but interacts with matter like a particle. This is very confusing, right? That light is simultaneously both a wave and a particle. It is always a wave and a particle. That is kind of our interpretation here. Um, that it travels like a wave and it interacts with matter like a particle. So if the way that you test is light a wave is examining it as it travels, you'll see wave particles. If the way that you examine is light a wave or a particle is by watching it interact with matter, Einstein tells you that it will exhibit particle behavior. So when it travels, uh, it it demonstrates wave properties. When it interacts with matter, it displays particle properties, but it always has both. That's this Einstein wave particle duality. And so here, when the light is interacting with particles, with matter, it behaves like a particle, right? Again, we're going to see that when we get back to the Compton scattering also. But um, Einstein says that Einstein says that the energy of a particle of light, Einstein didn't name a particle of light a photon, but the energy of a photon is h times f. That's even crazier, right? Um, the energy of a photon um, depends on the frequency. Particles don't have frequencies, waves have frequencies. But Einstein tells us that the energy of a particle of light is this Planck's constant, again, that's 6.626 times 10 to the minus 34 joule seconds, times the frequency of the wave. Um, it's also equivalent to hc over lambda, right? Because c is equal to f times lambda. So f is equal to c over lambda. The energy of a photon is just hc over lambda, um, where hc is a value that we'll use commonly enough in this class that let's just define it now. 1240 electron volts times nanometers. Um, and Einstein's going to tell you uh, that there is some work function. This phi, the work function, and it describes uh, kind of the minimum energy required to release uh, an electron from the metal. And so now Einstein is just relying on conservation of energy. You have this input energy from the light, h times f, and you have this energy debt, phi, the work function. And so whatever energy you spend to free, so you start with hf to spend, you're spending some of it to free the electron, anything less left goes into the kinetic energy of the electron. So why do we say Ke max? Well, again, coming back to my bad little pictogram here, not every electron has the same easy way out, right? The easiest ones out will have uh, will have the maximum kinetic energy. But this one, which had to kind of struggle to get to the surface and then escape, it will have some energy less than the maximum kinetic energy. Um, so Einstein gives us this statement that uh, the photon energy minus the work function to liberate the electron, the energy to liberate the electron should equal the maximum kinetic energy. And that, notice, uh, if you were to plot kinetic energy on against frequency, you would see that uh, the you would see the following, um, that this is just a linear relationship between kinetic energy and frequency, um, that as we increase the frequency, the maximum kinetic energy of the photoejected electron should also increase. Which, note, is one of the things that we needed to experimentally explain. It also explains why you have a dependence of uh, the photoejected electrons, whether they're photoejected at all, based on light frequency, right? Because if HF is not equal to phi, if it's less, right? If HF is less than phi, then KE max uh, will be zero, right? Uh, you won't have photoejected electrons. So there is some minimum frequency such that HF is greater than phi to allow the electron to escape. So Einstein is also able to explain uh, why there is a dependence of ejection of electrons on light frequency. He's also able to explain why there's basically no time interval between when the light arrives and when the photoejection occurs, because you can think of it as raining particles of light, and each particle, each photon, either has enough energy to liberate that electron or it doesn't. Um, and so you can heat up the metal, but uh, but the electron either is instantly freed in its interaction with the photon or it's not going to be freed. And so there is no time interval delay. Um, it also explains uh, why more electrons are ejected by bright light. In Einstein's description of this, uh, thinking of it like rain, right? A bright light is like a heavy rain of photons, and a dim light is like a light rain of photons. Um, so more uh, more intensity means more arriving photons, means more electrons can be ejected. A dimmer light means fewer arriving photons and thus fewer ejected electrons. And so um, Einstein wins the Nobel Prize for this because this was very uh, easy to experimentally look at. In fact, uh, the the work functions for uh, for metals, um, sodium 2.46 electron volts, aluminum 4.08 electron volts, copper 4.7 electron volts, zinc 4.31 electron volts, silver 4.73 electron volts, platinum 6.35 electron volts, lead 4.14 electron volts, and iron 4.50 electron volts. So as our first little example here, um, if we illuminate sodium uh, with 300 nanometer light, what is the maximum kinetic energy of photoejected electrons? Well, um, we can uh, uh, we can look at hc over lambda, right? That's the energy of the photon. So 1240 electron volt nanometers over 300 nanometers minus the work function for sodium is 2.46 electron volts, um, is approximately 1.67 electron volts. So the maximum kinetic energy you would expect under the Einstein model of the photoelectric effect is 1.67 electron volts maximum kinetic energy for a photoejected electron if it was photoejected by 300 nanometer light. What's the critical wavelength? What is the minimum uh, wavelength of light that will still allow uh, photo ejection of the electron. Well, all we're going to do here is we're just going to set the critical value to when the kinetic energy goes to zero. The maximum kinetic energy goes to zero. And so we're going to say 0 is equal to hc over lambda critical minus phi. And so you can solve that for lambda critical. It's just hc over phi, 1240 electron volt nanometers divided by the same work function of 2.46 electron volts yields a value of about 504 nanometers. So, so if you uh, try to use a longer wavelength than 504 nanometers, it won't have enough energy uh, to uh, per photon to liberate an electron from sodium metal. So, all right, this I was trying to keep a little shorter than this. I will stop here, and then our next lecture will be on the Compton effect. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow.